Hello, everybody, and thank you for joining us today. We're excited to bring you this webinar and talk about fleet management automation for delivery services. Obviously, fleet management automation can mean many things for many different companies, whether you're managing a fleet of cars for delivery service, or you're managing a fleet of vehicles for transportation, you're managing a fleet of vehicles for a company, vending routes and things like that. There are a lot of things that go into automating your fleet management services for optimizing delivery, optimizing profitability, and optimizing the efficiencies with which you operate your business. So we're very excited to have two of our senior people, our project manager, one of our senior project managers, and our delivery manager, who themselves have decades of experience working within this industry and working with different clients and partners on their fleet management needs. First up today, we have Konstantin Demishev, again, one of our senior project managers, and he's going to be talking about the various features that go into fleet management solutions and what kind of features are necessary for optimal performance in those delivery companies. So I'll be talking about feature sets and functionalities. Very excited to have you with us today, Konstantin. After Konstantin, we have Sergey Shalayev. Sergey is our delivery manager, and he's going to be talking about the actual route optimization. And again, route optimization has a lot of different facets that go into it. It's not just as easy as how do you go from point A to point B and point B to point C, but how to increase those efficiencies, how to do it with minimal impact to your business in maximum optimization, whether you're trying to monetize it, whether you're just trying to optimize the timeframes for delivery. There are a lot of different things that Sergey will talk to us about as well. So very excited to have Sergey with us too. A little bit about Archer as we get going. Archer Software has been in the software development space for just about 20 years. We're a professional services and custom software development company specializing in helping startups and enterprise companies digitize their automotive domains. And Archer has a lot of experience across the automotive domain, working with some of the very biggest companies in the industry. As you can see here, some of our clients, including Volvo, Renault, Green Roads, Cantaloupe Systems, M Food, and Get Package. And these companies are all very different, from actually being out on the road for moving their fleets of vehicles around, to delivering packages and delivering food, to tending to vending systems. And how do you plan those routes when you have vending systems all over, some that need more immediate tending to, but maybe further away? And how do you take all of those different feature sets and make it the most efficient as possible? So first up today, we're going to hand over the mic to Konstantin to share with us the feature sets that are important when you're looking at fleet management solutions. So, Konstantin, you're up.
I hope you may see my screen now. And
yes.
As Brian said, I'm a product manager for Archer Software, and today I'm going to cover some topics relating to make your fleet management more effective. Before we start, I'd like to highlight a couple of things that there is no identical delivery businesses, and even when it comes to food delivery across the world, all they different. And even if you operate in different locations, you have to see the different business rules related to routing, related to price policy, related to maintenance of your fleet. And that's why I'd like to treat this event like share approaches which we introduce in our client businesses rather than to ready-to-use actions. To start, let's set the context. I will cover the journey of two our clients. The first one, it's food delivery service startup, And this startup has its own fleet. They operate in the short delivery range, like 4 to 6 kilometers. And the peculiarities that, in all food delivery services, the routes are known at the beginning of the workday. And the opposite of that, another our client, transportation company, they use primary freelancers on their routes, and they have a middle range delivery like 15 kilometers. But their peculiarity is that delivery and pickup points are known at the beginning of the day. And so we will see the approaches of these two companies. And as I mentioned before, the environment when you operate is a crucial factor as well. Both of them operated at the resort town, which has like a rail layouting, and their city center looks like Manhattan. And another environmental peculiarity is that the lifestyle of the city is very sensitive to weather due to coastal location. It means the rain may affect the delivery service pretty much. So both of this company actually have the same approaches when it comes to make their fleet more efficient. The first one is, of course, maximize fleet utilization. If we have a vehicle and at this particular time this vehicle does nothing, it means waste for our business, because our business is growing only when the vehicle on its road. The second one, it's fleet maintenance. If our vehicle cannot operate because it's broken, it means waste for us as well, and it's a direct use of profits. And the third one, it's of course routing optimization. And I will cover first 2 points, and we'll touch briefly the third one, but Sergey will share more information on the routing and its optimization. When it comes to delivery service, it's pretty much from the helicopter point of view for all delivery service companies. And there is the process which looks like this picture. And there is a transportation part of the process when vehicle on its road, and it brings a package to the client. However, around that there are a lot of different activities, like travel time to pickup point, like waiting at the pickup point, loading or unloading time, waiting at the delivery point, and etc. It may be some regular actions like sign some document. And the idea to increase utilization is to decrease all process steps which are not related to transportation itself. We treat them like a waste, and we would like to increase the ratio between value-added activity like a transportation and waste. Yeah, the approach is pretty important as well, because we have to move the time of waste activity to 0, but do not touch transportation as well. And there are a number of options how we may do that. We of course may ask people to load faster or to wait less, but it hardly can work in our reality. And there are a bit more reliable options. And the first of that is, of course, optimize our routing. The second one is the correction of the vehicle type, because it doesn't sound reasonable to use truck to deliver the pizza. And the third time, a bit from the human perspective and relationship perspective, it's an improved collaboration between our suppliers and recipients. And I will show some number and may say that for food delivery service especially, the huge improvement we've got exactly here rather than optimizing routing or choosing appropriate vehicle type. When it comes to optimizing routing, we pay attention to the layouting of our operation, city layouting. And for instance, we've got a number of cases that it looks like we try to optimize every step, but at the beginning, the lead time of the service is increasing. And you may see an example when we have two roads, and the second roads has a bigger time to pick up, but at the end, due to the low transportation time, the overall service time is less. It works, you may see such pattern for the locations when you have Manhattan-like layout, is when we have a lot of one-way streets, and the vehicle should do unnecessary turnarounds and wait on the traffic lights on its road. Sergey will cover a bit more about that, and I will move further to the correction of the vehicle time. We found due to our data that transportation time was been increased on weekends, and we analyzed many of factors and just suddenly got that the city center, when we operate, is closed for petrol vehicles during weekends, and it means that the vehicle should change its route, and we took this into consideration, and we changed our scooters to e-bikes, which could operate in the city center. And another thing, it's as I mentioned before, the correction of the vehicle type depends on capacity. When the business started growing, the content of delivery may change as well. For instance, when we started our food service delivery, the first clients was pretty cautious, and they ordered like a couple of pizza, and that's it. And the average order was like 2 to 3 items. But as we started growing, the package, the content of the package was changed, and the blanket kind of package is a regular thing for us. And we took it into account because, for instance, if you would like to deliver 15 pizzas, it's hardly be possible to implement by bike, and you have to have 2 bikes, which make delivery more complicated, since food delivery is pretty is pretty accurate service, and the perception that a client receives from the rider is a key factor of the delivery as well. And no one wants to get the same order by 2 or 3 riders. They would like to get whole package at the same time. And we started introducing capacity approaches, and assign vehicle to the order depends on its content, which make our logic a bit more complicated, but the benefit which we get is crucial. And the next thing which I'd like to cover, it's delays in the pickup location. As I mentioned before, when the vehicle waits for something, it's always waits for us. And orders wait at the restaurant to take this order and start transportation. It's pretty crucial for us. I got some numbers from our system, and as you may see, D&J has an average delay time like 12 minutes, and it's a crucial number for us. It's like a quarter of our service time. Our service time, average service time now, it's 40 minutes. And it may affect our routing planning pretty much. And we started introducing some delay coefficient based on historical data for our clients. And when we calculate our routes, we use this coefficient. But we had a challenge with that because time to time our discrepancy between expectations and reality was so big that it harmed the business. In food delivery, it's pretty important. For instance, if you order the pizza should be delivered, should be hot when it's delivered. But in these cases, the delay index brings some harm, since a pizza or any kind of hot food can be cold when the rider arrives at the point of destination. And we started to see more deeper, and we found some interesting dependencies. For instance, the first one was pretty obvious, but again, you have to feel in your business that these hypotheses can work. The delay time depends on the day of the week. And for instance, the first chart, you may see that our Saturday delay time is different from the Friday delay time. And we introduced the day of the week in our model. And we've seen some benefits based on the feedback of our clients. However, time to time, we continue getting such kind of issue, and what we found that the restaurant may run some promotional campaign, and this campaign increase amount of orders, and delay time is increasing as well. And we changed our machine learning model, and we introduced the promo. For instance, you may see the chart when the restaurant introduces breakfast promo, like some discount on the breakfast. And we started feeling benefits of this one as well. And the another insight was that environmental factors may affect us. For instance, as I mentioned before, our delivery area at the coastal, and the rain or snow may affect transportation across the whole area. And we found that when it's rainy, the amount of water is increased, and we have to take this into account as well. And our model got another environmental factors. When it comes to our model, it has some sort of evolution, because the first thing, it was just for statistical approaches, when we took some number, calculate some mean, and add this mean to our routing calculator. But more factors started affecting our business, and the just a linear model didn't fit us. And what we do, we started thinking into the approaches of machine learning models, and currently we have the evidence that it pretty helped us, because amount of factors which we have like 7 right now, and they do not have linear dependency on each other, and the model continue progressing. And for instance, there is that's how our model looks right now, and you may see that some things like a day of week, season, it's pretty obvious, but another thing that affected our businesses was how restaurants do their promo activities. We took it into account as well, and what kind of food type is popular right now, and what kind of food contains into the order. It affects also weather, as I mentioned. It appears as a crucial factor for us, and we even decrease the radius of delivery when it's raining. And also the market state affected us. For instance, density of similar restaurant delivery area may affect the wait time in particular case. And for instance, if you have pizza and there is another place, then people may order pizza in this delivery radius. It may affect both restaurants, and all these factors have to be taken into account. And as I mentioned, our model for delays continues growing. But the crucial thing here is that we started from the beginning. We started from the pretty small and obvious, and then as soon as we found that some forecast doesn't correspond to the reality, we have rule of thumb that as soon as happen, it means that there is another factor that affected. And we just add the factor to the model and rebuild this model and see if we are right or not. And it means that at the same time we may have this number of models for the same indicator. And for instance, we have delays, we have indicator of vehicle reliability, I will cover a bit later. And we have also predictability demand, which we use for the fleet management for marketing approaches. But again, we have to see the whole business, and the fleet management is just a part of this business. There is a marketing which affects fleet management, and there is some operational stuff which happens in the office, and this affects fleet management as well, and so on. Good. That's how our clients utilize the machine learning for their purposes. But again, all delivery services are different, and the approach which we find we would recommend to use to everyone. But the number of factors and which indicator is crucial for us, and what kind of waste you have in your hypothesis, it has to be defined on the client side during some sort of discovery phase or similar research. And yeah, and then another case again for delivery, and we find that people, when they order the food, they do not see kitchen when this food is cooked. And but when we deliver for instance, a box of pizza, they got of perception of clearness of the kitchen or quality of the food. We are vehicle that bring this package. And we had some research, and we saw that users that received the package from the let's call it clean vehicle, right? They rated the food much more higher than other clients, despite of the food is the same. And we got that appropriate maintenance allows us to keep our operational expenses in desired mountainous, because again, when you have operational expenses, you do not see this as a dry number. This should correlate with utilization of your vehicle, because expenses on the vehicle and how this vehicle is utilized, there is a correlation about it. But the issue that we got that usually mechanics and clean services, they work at the same time as our service. And it means that you would like to do some maintenance with the vehicle. This vehicle should be taken out of the road and sent to the garage, which is not appropriate for us. And we decided to, after analyzing some data against a model, we decided to change this approach. For instance, we've got some our distribution, how our vehicles is utilized during the workday, and we see that there is some gap between like 1 p.m. to 6 p.m. when we have decrease of demand, and despite of it's pretty difficult to book these hours for maintenance, we decided to do that. And we sent all our, not all, but some of them, some scheduled vehicles to the garage to maintenance procedure. It would be just a cleaning, or if it e-bikes, it would be charging, and so on, so on, so on. It's likely that such pattern can be similar from day to day, and it means that naturally we get the schedule of our vehicles, and this procedure works better than the classical one, and we decided that if vehicle is not on the road, it should have some sort of maintenance procedure. So we do maintenance. The model helps us to come to the solution that we have to do maintenance when it's possible, but not when it's time. We also found that expenses go up, but it's still in our budget. But some reliability index goes up as well, and we continue growing this model, and we don't deny that this model is so complicated, as I showed in delay model. But yeah, nevertheless, we found that some statistical data put in the appropriate machine learning model helps develop the client business. So, and some takeaways about improving or boosting your fleet management by using machine learning approaches, that there are much more factors that affect our business than we think. As I showed before, the weather happens crucial, and the change the market competition is crucial as well, and so on, so on, so on. And as soon as we've got the prediction doesn't correspond to our reality, we try to find more factors for our model, but we don't deny that it could be a mistake, and it means that we have a number of models which works together to correlate, to do Right. That's yeah. That's what I was going to share with you, and the journey which we pass with our clients. And I hope some of these ideas may have practical applicancy in your business as well.
Thank you, Konstantin. If I might share with the group, if anybody has any questions, please feel free to drop us a note via chat and we can answer those questions for you. Konstantin, I have a couple of questions for you. One, when you're talking about maintenance needs, when you're building a fleet management system, have you come across clients where you've been able to automate the maintenance systems from the car via the OBD or some other systems so that you can actually work into the fleet management planning when a car actually does need its service, when it's coming up for service needs? So is there any kind of integration and automation that takes place so that the fleet management operator knows, oh, this car is going to need an oil change next week. Let's work that into the plan in advance.
Mm-hmm. Right. From our clients, each of them has its own custom developed system because, as I mentioned, they may have own fleet, but this then can be leased, and if it's leased, the maintenance covered by third-party company and so on. But of course, every vehicle has their schedule when oil should be changed. And what we do, we see if we could do it right now a bit in advance, rather than to do it after its deadline. And yeah, that's a point when we get some increase in expensive, but nevertheless it works. Right. When it comes to maintenance system, I would say it's custom solution.
Excellent. You also spoke about weather and how that comes into play when you're working with a fleet management system. Do you take real-time weather data and pump it into the system and analyze it that way? How do you account for a storm coming up in the middle of the day, last minute, or things like that?
Yeah, right. We have integration with a number of weather services, and just to take their data and put in our system for forecasting and for real numbers as well. But again, we found interesting insight here that the forecast service should be the same, because if you build your model and you use service A, by try to build the forecast and use service B, you may get some unpredicted number. And that's why we just run our machine learning model in our cloud environment, and we actually took it from the different services. But when we do calculation, we calculate based on just the one, like give me prediction on the service A, give me prediction on the service B.
Great, and then you can affect the route planning based on that data.
Yeah, right. It actually it affects radius of the delivery, but radius of the delivery is the one of the component of the routing plan. Right.
Got it. Makes sense. You also spoke about promotions and how that can change the number of deliveries taking place for a delivery company, a food delivery, let's say. So I'm assuming those promotions have to be put into the system in advance so that the system can optimize, knowing that there will be a larger number of requests and deliveries being put out there.
Yeah, right. It's like it's a two-way game, because when you deliver some food from the restaurant A, for instance, they do not want their food come to the client in the cold form, right? And they want the delivery works well for them. And we have an integration when the restaurant may indicate that we are going to do promotion like next week, Tuesday from 10 to 11, and it's going to be breakfast promotion. And some of them even may share their marketing expectation from this promotion.
Mm-hmm.
And yeah, it worked in this way. But again, suppliers, they would like the delivery service works well as well. Because if delivery service fails, it's not a fail of the delivery service, it's a fail of the service, like a big whole. Supplier, I mean restaurant, and the delivery company.
Right. Yeah, because the food delivery service, someone going to pick up the food, if the restaurant doesn't have the food ready and they have to wait, it's not the delivery service's fault, but the route planning might have to be altered or things like that. One other question for you, and Sergey, you might have some feedback too as you speak about route planning, but what about refueling? And so you have electric vehicles, you have hybrid vehicles, and you have fuel-only vehicles. Obviously, the electric vehicles recharging stations aren't quite as prevalent as gas stations. So do you work that into the fleet management platform?
When we see, let me show this slide. When we see that we have a lack of utilization, we do maintenance. Maintenance means refueling as well. For instance, if you have an electrical vehicle, it's a time to charge them. When you come to a gas station, it's also time as well. We do not put refueling in our some transportation period or so on. For instance, you cannot pick up the package and to go to refueling, right? We would like to do this separately.
That makes a lot of sense.
But it's planned. For instance, if we have like a Friday, the second part of the day, it's dead time for us because it's a resort town and no one is eating, everyone is walking around, and we decrease our fleet capacity here, and we calculate if we should do some sort of refueling or not. Right.
Right.
All this data, all this forecasting, all this routing, they are in the platform.
Excellent. That's great. A lot of great information. Thank you very much. Does anybody on the call have any questions? If not, you can always ask questions later too, but if nobody has any questions at this point, then I think we're going to hand this over to Sergey, who's going to talk about fleet optimization and how that all comes into play. So Konstantin, thank you very much. And now, Sergey, we'd love to hear from you and your experiences and expertise.
Okay, so I was tasked to cover this quite a huge piece of science in half an hour, and describe what are, at least to give some grasp of the flavor of the routing optimization, how it works, how we deal with it, why we need it. Basically, question-wise, pretty simple. So, if you like a transport company or delivery service, anything, so you want to maximize your revenue by increasing the number of jobs completed, and you want to minimize your costs by reducing the total cost of routes your vehicles traveling by. So it's pretty much like this. No rocket science here, but a very important point is that all the optimization works much better. It's all about the costs and the total costs of route, of a group of routes, of solutions. To start with, and for you to get understanding what is all about, I suggest to start with the simplest possible vehicle routing problem, and actually processors, the common processor from the class of the problems is a well-known traveling salesman problem. So it's pretty straightforward. You need to find the shortest path through the set of points. And at glance, it may seem like not very complicated task. You see here, we start here several points, so you need to, connect them somehow to get the shortest route. Actually, you can do it manually and like this, using the Google map. Here is these points, and you just can like toss them around and see what is the distance you're getting. So, and with the 3 points in the route, you have like 6 combinations which you can test easily and find your solution. Okay, here is a solution. I did this work for you. Pretty simple. This is pretty simple. So why is the problem? It seems like straightforward and pretty easy to solve. Here's the other one where I have added a couple of interim points. Here is a solution. How it's different from the previous one? Different, very simple. Here you have like 120 combinations which you need to check, which doesn't look like a practical task to do it manually. Though it's still like comprehensible, you can do it with some programmatic, some code and stuff. But 5 points it's quite a small number. And here we come to the main problem actually of the routes optimization. It's a which I call factorial course. I don't know your math background, but general factorial is a like computing this, multiplying each member of this of the number sequence. Like 5 factorial is 1 multiplied by 2, multiplied by 3, by 4, by 5, and it actually grows very quickly. You can see here. So if for 5 elements we have 120 combination so-called permutations in combinatorics. So for 10 elements, we'll have this quite a 3.5 million of combinations. For 20, it's I don't know how this guy is called. I mean this one. And you can see even for a relatively small amount of elements, which is 100, you have this is some very huge number. So it's probably there is no chance to test them all and solve this task. And of course, the brute force approach, which means that you check all the possible combinations, it's not the way to do it. There are some algorithm which helps finding exact solution in the smaller time. It has complexity lesser than brute force. Actually, here I want to just like apologize for those who know what is big O notations. I put these calculations here just for an example to see how huge becomes the how many operations required to run pretty simple, like to solve pretty simple traveling salesman problem. So here we have it's comparing to the brute force. This is more relaxed. You see that it's not going so fast, but it's still going fast. So and 100 elements, it's already have 10 and powered by 30. It's better than 10 powered by 157, but not too much. Actually, if you pay attention, you see this number here. It's just for the reference that you can compare these numbers with these. It's actually a number of nanoseconds passed since the Big Bang. So the total time of universe, actually. compare this. Doesn't look like it can be done at all. However, it can be done. For now, for example, first of all, there are specific architectures of processor units which are aimed specifically for solving traveling salesman problem. It's Concord TCP solver, and the latest record, it's about like 85,600 cities problem was solved. It's spent about 150 something like 150 CPU years. Not really much helping in. I mean, I doubt anyone would buy these specifically tasked computers and spend so much of computation power to just solve this task. But what should we do here? So if it's kind of unsolvable, how we can deal with it, how we can continue working. So, and furthermore, when the traveling salesman problem itself, it's though it has some practical appliances, it's a electronics circuit designing, it's a DNA research, but in terms of our main topic today is the fleet management, it's not very applicable. So there is a generalization of traveling salesman problem. It's a vehicle routing problem, which combines several the number of TSPs and extend with additional feature. First of all, it's not one vehicle used, but it's a fleet of vehicles which can be finite on infinite size. It's a real world constraints like time, schedule, and capacity dimensions. So you don't have, vehicle with unlimited capacity. So, and you need to take into account not to send the man with a bike to move a refrigerator. They're pretty obvious and straightforward and natural. There is a more complicated, usually it utilizes a lot more complicated cost model, is the TSP in traveling salesman. Usually distance is the distance equals the cost. In business-driven cost model, it may be a lot more complicated. I will get back to it a lot later. So there are normally if TSP consists of single sites which need to be visited, and so the vehicle routing problem usually have standard pick up and deliver. You need to go there, pick up some cargo and move it to the other location. And there are actually a lot more differences and a complication and extension to TSP, which not making it any easier to solve. And the main things that in real world, in real business, you typically have a bit more jobs than 100. Here it's as I remember, it's about 800 deliveries ordered. So, and you can see this routing around them. So how do we deal with them? How do we skip these factorial curves? In general, there's one solution. It's a heuristic. It's a set of algorithm. I will try to explain it. This is pretty simple. It's a technique designed to solve a problem more quickly when classic methods either too slow or finding solutions which are close to optimal, approximate solutions which are close to optimal when the classic method of finding exact solution cannot do it. It's the whole family of different algorithms, approaches. All they have in common that you trade off some optimality of the quality of the result. So you do not finding the best possible solution ever, but you have finding solution good enough in a lot more reasonable time than lifetime of the universe. which makes it actually usable, totally usable for practical business appliances. Some I need to dig a bit deeper into these heuristics, just because it affects like some business approaches, which we will talk a bit later. So some example here we have the. Let's get back to the TSP for a while, just for demonstrational purpose. Here's a TSP. It was taken from TSP-lib. It's a specific library which has like instances of TSP with known best solution. So this one in particular, here's 100 points, and it has best solution found for now is 21,282 units. And so I just to remind you that 100 points means this huge amount of permutation. It's 157 here is a power of 10, and basically, if you would try to just find the best solution by checking all possible permutation, you will probably fail. Here you see. But with heuristic, you can achieve pretty good results. That's actually practical. It was practically solved in very reasonable time, I should say. It's less than a second. I've got the result of 23,032 units, which is just 8% worse than the best known solution. So it's, you know, this small trade-off of 8% is I think it's worse of spending universe lifetime versus less than a second. And actually, this was done by very simple, you know, it was like a academic realization of simulated annealing. Is one of the heuristic algorithm, along with K-opt's algorithm, which also, let's say, it's very simple heuristics used here. So it's actually knows nothing about, you know, different stuff about practical essence of the task. It works very, you know, straightforward. You see, first, let me get back one slide. So this is just a random sequence of these points. It takes the first initial solution, then start doing following. So it just takes a random segment of consisting of k elements. I don't remember exactly how many. It's about 10, I guess, or it's a 10 or 20% of the total amount. So randomly placed within this sequence and just shuffles it. After that, it calculates the cost. If the cost is better, if it's lower than previous one, this one becomes new best found solution. Here is some specific tricks that it uses probabilistic approach, and at some moment it can accept solution that it's worse, just not to stack in the local minimums, but it works as simple as that. So at each turn, it takes a random segment, shuffles it, check. Take another segment, shuffle it, check. So I can demonstrate you in like in dynamics how it works. Let me see. One second. Yeah, let's get back here where I started. Here is the same TSP uploaded here. So how does it search? You can just watch on your screens. You see it's just at the beginning there are each next solution usually is better than the one was before. Then it's start slowing down. Actually, this calculation right now is like 1,000 times slower, just for demonstrational purposes, just for the sake of the rendering, that you could see how it do the job. So when something changed to the, when use good solution accepted its render, so you see it's moving forward, slightly reducing here. As you can see, that is a minimal cost, like best cost for now, and you see that it's slowly going down. So in fact, even with this slow demonstrational thing, it will work like a few minutes to get to the end. So the point I want to stress here, that the algorithm itself doesn't have any specific logic. It doesn't look for like crossing, which is when the edges of this, let's say, graph are crossing. It means normally means that they are not placed correctly. It doesn't do anything like that. It doesn't do any clustering, trying to any using like nearest neighbors or something like that. So it's it's clear from any kind of business logic. The only thing it has injectable cost calculator, which can be replaced by some alternatives. But this one is just calculating the total distance of the full route, and there is no sophisticated filtering adjustments, nothing. It was done just like to check how the simulated annealing works, and actually it works kind of good. You see, it's slightly become more rounded. There are no loops that disappearing, and the price at the point. By the way, right now the length is 22,675. It's even better than I've got in my presentation. So this solution is just a few units away from, let's say, be honest, a few hundred units away from the best one ever found. It was a problem consisting of 100 points. I think it's pretty like self-explanatory. So very simple algorithm, works really fast, and getting the solution of something that is very hard to solve exactly, it finds a solution which is not the best, but it's good enough to live with. Okay, let's back to our presentation. That's about the heuristic and what I wanted to tell you about it, because it's quite a complicated topic and requires a large discussion. So, but there are several like key points which you should know. First of all, everything dealing with routing optimization, it always deals with NP-hard problems and requires it. Even the heuristic algorithm are not that, not that performant. So if you put the task of like several thousand of points, it would take its time to solve it. So it's normally that there are huge amount of computations required. So the performance is always, your unforgettable, inevitable fall. So you need to fight with it on all stages. Another point is here, which I wanted to stress, that as you saw in that algorithm running and solving, that there are not so many logic in optimization, like in the routing itself. So it's typically done without really without real appliance to the geometry of the route or something like that, but without any vectors, directions. It may increase improve performance, it may yield the better result, but in general it's not actually required when you do it with heuristic. So here this slide will present like what are the hidden caches actually working with such algorithms, implementing them, using in practice, it's kind of, there are several significant differences from what you could get used to working with normal software development. So, and they are quite crucial, and sometimes people do not understand how it can be, but it's something you actually need to embrace because it's inevitable. So, first of all, due to the probabilistic nature of heuristics, it's not so it's not consistent enough in yielding result. You can use same problem, same algorithm, same everything, and got a different result on any try. So it mostly depends on the nature of the problem, how it's formulated, what are the jobs inside, what are the constraints inside, all that stuff. If it's a huge problem of like 1,000 jobs and like 200 of vehicles, you would probably never be able to tell how close you are to optimal solution, because optimal solution is not findable at all. So, so you may the only way to check how your implementation, your particular algorithm works is to take the library examples. There are not many of them, but quite enough. So, and you can benchmark your realization, your implementation against the known best results. So, and you should believe that if you get the results that are good here, so basically means that it works good. On the real practical problems which you put, you will never be able to tell it. Next, specifics which bothers and actually is a kind of pain here is like when you if certain specific condition within your implementation leads to the failure, it will be the hell and high water to try to might appear really challenging to debug it, because actually this particular state might never be reproduced. I mean, never. If you know 10 power 157, it's something that it's a huge amount of potentially possible states. So at some point, you need to just use statistics here as well. So if it happens often, then most probably you will reproduce it. If it's happened once, there is no guarantee that you will be able to find what was the problem at that point. As I told before, even though heuristic is a lot more performant, it's like typically big O complexity is n log n multiplied by log n. So it's pretty, it's not that complex at the exact algorithm, definitely not that complex as a brute force, but it's, however, it's still complex. So you're dealing with iterative calculations, which runs like millions and hundreds of millions of times. So at some point you may find yourself checking how many micro or even nanoseconds certain operation takes to run. So, for example, at some when using just simple spherical distance calculator, I found out that caching is not helping at all, because taking the cached value from the memory took like a 25 microseconds. Taking the calculating it again, it was no, not 25. It was nanoseconds. Like this, it was 250 nanoseconds, and calculating was like 190 nanoseconds. So, you can work in development, software development for ages, but never dig that deep into the performance issues. And you actually, it would be the matter when you're working with routing optimization. Also, this probabilistic nature actually make it kind of challenging when you need to scale, because when the solutions are evaluated using some physical probability formula, like it does in seam annealing, or random mutations, like it goes in the genetic algorithms. It doesn't matter much how many things are done in parallel. It affects the performance, but not that crucial. For example, I was trying, like, running the same problem of 800 deliveries with in one thread, in two threads, in four threads, and then growing up to, I think it was like up to 64 threads in parallel. It was just like, we rented the Amazon Web Services computational instance, which costed about like $20 per hour. But the growth between one thread and two is like, it's actually 2 times more performant with a 4 thread. With 16 threads, it was the growth was not linear at all, slowing down with a number of rising. So there are not so many places where the doing the thing concurrently brings a improvement. And the last, perhaps, specifics, but not in the least, and perhaps I would say is the most important specific here, is that algorithms and like this part that actually does the heuristic magic, it's usually, it can be quite completely complex due to the number of entities involved. So it's different constraints, different rules, all that stuff. But in general, it's pretty normally it would be pretty abstract. So, and like, it won't normally it won't know anything about the business logic beside what you put as a constraints, injected as a constraints, and we'll do that just the quite dumb job like the algorithm I displayed you. Just select random subsequence, shuffle it. Select random subsequence, shuffle it. So no, like, it's not very intellectual stuff. So and the efficiency, efficiency of the and the optimality of the solutions achieved in most cases depends much in bigger scale on the how the actual problem was formulated from the beginning. So if the problem is formulated like it's the same conditions, like same set of vehicles, same set of jobs, can be formulated in the wide variety of actual VRPs. So you can consider like a mixture of shipments, service, something you can consider as being as initial row, the way you declared your cost model, all that stuff. There's a lot more influencing performance and solution quality than actual algorithm that works. Even the dumbest implementation of simulated annealing, as I showed you, does the job quite good. I should say performant and good. So the problem is that how you prepare the data input. I don't know, Brian, I'm sorry, do we have more time on it? Because I'm like on the hub where I can break, or and we'll perhaps do the next webinar to continue, or I can continue right now.
I think you can probably continue a little bit more.
Okay, so something about how actually the roads are built, what vehicle routing problem consists of. So definitely it's vehicles itself. It would be strange to try to solve vehicle routing problem without them. It's a jobs. It's a here we have some specific language, which is like a legacy language. I don't know actually where it comes from, but so there are two types of jobs. It's a shipments. It's a like jobs with two locations. So it's a you need to go to location A and pick up the cargo and go to the location B and drop off the cargo. So that's what we call shipment. Services is a job with one point. Usually, typically, it's like you have a depot where you load all the orders and then just go and deliver them to several locations, or vice or opposite. You like going out from the depot and pick up the cargo from different locations, then you return back to the depot. So that is services, one point job. Constraints, that actually what the way how the business rules and some real world conditions are applied to the problem. So it's the most obvious are time windows, time schedule of the vehicles itself and the jobs, and perhaps capacity, because it's inevitable. So you always have limited capacity. So these two constraints are natural, and but there can be a lot more different business specific constraints which can be applied. And finally, it's cost calculators, which as I said at the very beginning, the key metric for the road utilization is the cost. So you need to do complete the maximum job, maximum number of jobs at the lowest possible cost. So the cost influences a lot. So because there are a lot of things that can affect the cost. It's a time, it can be distance, it can be waiting, idle time, or like this stuff. So let's go. Oops, sorry. Let's see. So let's say we're starting from formulating the vehicle routing problem. We have some jobs. We have the question here is about like formulating the job. Do we need all this stuff? Definitely, you need the jobs. That's pretty obvious. If there is no jobs, so nothing to build the road off, or no, doesn't have any sense. If there is no vehicles at the moment you're trying to formulate the job, in some cases it might be possible to build routes without knowing actual location of vehicles, and I will show and explain how it can be used in practice. Constraints. Constraints are pretty important because, and I will show it with examples, because when you do not apply any constraints, you move the problem description quite far from real life, and most likely the solution you will get will be as much far from the life conditions as the problem was described. Cost calculators, definitely. If in any case, with any configuration, you need the way to calculate how much this particular route will cost, how much the total solution will cost. So without cost calculators, nothing will work. So at least it should be like as simple as for traveling salesman, like 1 unit of distance equals 1 unit of cost. So vice versa. 1 unit of cost equals 1 unit of distance. But it can be a lot more complicated, of course. And perhaps it should be if you want to get. So main principle here, as much as you, the closer you do the problem description, closer to your real life condition, the more easily you will be to apply a solution that you will get. So let's say, imagine somewhat, for example, if we are trying to build routes without knowing where vehicles is. So the problem is here that you can do some, let's say here we have 5 deliveries. So blue are the pickups, green are the deliveries. So you can calculate a route from some random point. Okay, you get the route, and with starting from this point, it perhaps will be optimal. But definitely, if you check, select another start location, the route will be quite different from the previous one. So, so in case you're you can do this, but it is kind of comes with a trade-off. So this particular route, it's better be recalculated if the position of vehicle would be different. But there is one case when you can build routes without the vehicle. Is when you have depot. So you have depot, you have like several types of vehicles in it, and number of vehicles you can operate with, and you know that all the operations start from the depot. So you either load cargo in this depot or just unload it at the end of the route. However, so with the proper solving of, so you can construct your vehicle routing problem the way that it will help you find, for answer the question, how many actually vehicle I need to serve these all orders. You see it here. So it doesn't need actual vehicle, because depot itself, it's like a it's a location of these vehicles, and everything else is just calculating how to distribute all these orders, all these deliveries into the vehicles we have. It might be useful in some cases for some business. Let's get a little bit further about the constraints. As I said, so time schedule and capacity are quite natural. So if you do not add them to the problem, the result will be quite kind of far from being real. So in this, let's see. This is a solution produced in this particular problem. There was no time schedule for vehicles and no time frames for pickups and deliveries. Looks quite a way where all the pickups and deliveries were added into the single route. Why it happened? Because actually for each next job inserted into the route, it might appear that it's cheaper to insert it into this vehicle than to the other, because they are somewhere on they're placed quite far from the center of event. So because there is no capacity restriction, you can load everything into the one vehicle. Because there is no time restriction, this vehicle may travel endlessly. So in this particular case, this actually, with this constraint, this solution appears the best of what system could find. So it's not an error. That's the way we formulated the problem and set conditions. Okay, let's add something, adding capacity dimensions to the vehicle and capacity demands to the actual shipments. So here it's kind of also looks strange. Right now is finally engaged another vehicle, but still not distributed over the these guys still standing idle. Why it happens? Because actually we're dealing with shipments here. So when vehicle pick up the cargo, its capacity dimensions decreases, with each pickup it decreases, but at some point it unload this, and capacity dimensions of the vehicle are increasing again. So it's possible to cover all these jobs. There are not a lot of them, and it's like 32 jobs just with 2 vehicles. Considering that there is no time schedule, that vehicle can travel endlessly, and there is no time limitations on the jobs itself. Let's add these time constraints into these. So at least we should add the time schedule for vehicle. They cannot, like ride endlessly. So but they have time of work, so it's natural limitation. And in this case, you see that right now system distributed job quite evenly, because in other way it would fail. No, again, just reminding that all the calculations are based on main principle: complete as much job as you can with least cost possible. So it will even, there is like an additional specific rule in depth, which actually you can add like penalty for not completed job, which also will affect the solution, because but actually adding just like simple constraints like time schedule to the vehicles, capacity dimension to the vehicles, made the solution much more realistic in this case. And finally, let's add some time frame limitation on the pickups and deliveries. In the real life, they are always there. So you can please deliver these. It's convenient for us that you deliver our package from 5 to 7 p.m. That's totally normal. And with this task, what you can see right now is that considering all the limitations and even considering the penalty for not fulfilling some jobs, it just doesn't fit. So quite a lot of jobs stayed out of the solution just because with these particular time limitations and capacity constraints and vehicle time schedule, the best what we can do is what you see, leaving quite a lot of jobs aside. But however, it doesn't mean that this is a bad solution. It's actually a lot more realistic, and actually, when applying it to real business, it would be much more correct way to go, much more proper way to go, because you do not, you will get the proper information, and you can base your decision making on it. So if in this case, for example, we can then take the vehicles from our partner, or we need to buy, if it's constantly repeating situation, we can buy new vehicles because we do not, our losses due to these unassigned jobs are huge, and it will be cheaper to get more vehicles, and so on and so forth. It depends on particular business we are using to. So, and the final, perhaps it's about the cost calculation. I will try to do it quick. This is a representation of the model we use right now. It's not like stone carved, but flexible enough, actually, as we know for now, to cover any business needs. So cost usually goes from several sources. So first of all, it's distance. There's, each vehicle type will have its specific distance cost, and it may differ due to vehicle type. For example, cost of distance on the bike and on the truck and on the van should be different. Time, again, it's like normally it's like a relation how how much money the unit of time would cost. These two are pretty straightforward and simple. But to achieve distance and transport time, there are different approaches. You can do it as simple as like crow flight lengths, just Euclidean distance between 2 points. It can be spherical distance on Earth between 2 points, and it can be some algorithm. It can be some engine that search actual direction on the map, and out of this direction get the distance to you. Transport times also can be different. So you simple solution usually involves like you are setting the speed of vehicles, you are setting some detour factor like for which can be achieved statistically, and you just multiply the distance on the I would say not multiply it, but you use it to calculate how much time it will take. So there is a fixed component which like fixed cost for each particular job, which doesn't depend on distance or time or cargo. There is you can specify the weight cost. It means that if the vehicle which is idle costs something for being idle, and service cost is time the vehicle loads or unloads. If it again for each particular business, the combination of them will be different. For example, if you're doing taxi service, usually operate only with distance time and fixed, where fixed is the minimum price that you pay, and distance and time is like the source of the total cost. But at some, for example, if you do like the furniture moving, whereas the service time loading unloading is quite significant, so here this component will prevail at some point. So at some point, different business implementation that may vary, but this particular scheme is actually for now, as far as we know, can cover all the possible variants of cost modeling. Crucial thing is here that proper describing of the cost model in the vehicle routing problem is extremely important, because all the system knows at what the cost calculator would tell you. So it doesn't know about the essence of things within the problem. It just knows that this solution costs N, this solution costs N. And if the comparing to the N with M with some probabilistic approach or whatever, if the M is better and it's best, so it goes. So, and if you incorrectly incorrectly configure the cost model for the calculation, will affect the results perhaps the hardest way possible. I think that's it from me, at least what I wanted to tell today. If you have any questions, I would gladly answer. Brian?
Yes. Sergey, thank you for all of that really great information. That was really wonderful. I have a question for you. When you're looking at the transport time and the speed, are you looking at the speed limits to figure out the time to get from point A to point B? Obviously, there are a lot of other factors that can come into play, from construction to weather, like we discussed earlier. But is it based off of the speed limit and the distance from A to B, or are there other factors that you account for? Like one driver might be just a slow driver in general and might always go 10 miles below the speed limit. And does the system learn about that individual driver and then factor that in? How does that come into play?
In fact, that is what I was talking about that, like a lot of things that we should leave behind the routing optimization algorithm. Because right now, for example, when solving actual practical tasks with huge numbers of deliveries, pickups, and vehicles, I mean, I was using very simple approach. So there is like a speed settled to the average 40 kilometers per hour. There is a detour factor. I mean, it's a deviation, potential deviation of transfer time, which is set like 1.3, and that's it. That actually would yield it would yield affordable solution. It will satisfactory. It will the solution difference in these nuances, like the traffic jams. Actually, it's traffic jams. Traffic itself is hugely overrated from my practice. I've gathered this stats about it. So the to take traffic into the consideration requires huge complication of the whole system, but yields pretty like it's pathetic results. I mean, pretty pathetic improvement. Though most of people, for some reason, are like very focused on that. So if you cannot get the traffic information, then the solution cannot be right. Come on, no. It would be perhaps a bit less optimal than it could be, but not significantly. However, the good question. So. In cases when you're dealing with, like slow-paced, or I mean fast-paced deliveries with a short distances, and where actually the actual speed of particular driver or actual availability of certain roads is important, then you should just put it to the to these two guys. So you can calculate actual distance from using map to using standard graph algorithms, and you can add the traffic situation as weighting factors on the edges of that graph from where you've taken directions. But it's all out of the scope of actual algorithm for vehicle routing. So it's implemented within the distance calculator. It's can be implemented. So it's all such things are implemented on the level when you formulate the problem, not when you solve it. And that was what I wanted to say. So, but however, important here is not to overrate the factors and their influences. And important not to inject these factors and processing these factors into the vehicle routing optimization itself. So it's like you need to distinguish, and it's very important that you need to distinguish between building the roads and preparing the data to build it.
Got it. I have another question for you. A few slides before, you were talking about the optimal solution, and knowing what, if you don't know your optimal solution, then you can't plan for it. But how do you figure out the optimal solution? Is that as simple as point A to point B to point C without traffic, and that's the optimal solution? Or what is the optimal solution, and how do you figure it?
Optimal solution is one that with the lowest cost found. So we're doing some heuristic magic, continuously improving. So as I showed you with a TSP, so there is an initial state with some random route, which is obviously very huge, very long, and then you do some heuristic magic and improving it step by step, and you can like run it. You can run it in my exact algorithm for this TSP that I was showing, it runs like 60,000 of iteration. You can and it produces a good result within the less than a second. You can extend it to the 100,000 of iteration, which runs like 1.5 seconds, and you will get better result, or you won't get, because due to the probabilistic nature. However, the idea is here that you have to believe and benchmark with on the problems with no solution. That's one of the most, hardly embraceable specific of this. So there is no way particularly to prove that this particular solution is optimal and how close it is optimal. You just need to rely on on the referenced measurements.
Excellent. Thank you for that. It's been great information. Does anybody on the call have any questions for either Sergey or Konstantin? Doesn't seem that way. And Konstantin, do you have anything to add to what Sergey had said, and vice versa? You guys have shared some fabulous information, really useful. We thank you both very much.
Yeah, just the one thing that I would like to add, that we started applying this approach with the costs to calculate what the optimal route is, because sometimes we had a feeling or hypothesis that it's better to delay something from the business perspective than to be on time, because cost of delay is less than the cost of delivery on time. And sometimes we do a hack when we delay our package, but we give some compliment to our clients rather than to do all our best to deliver on time, but with no significant profit to the business. And the first run, and it looks like it works well.
Actually, it's a good point here. For example, if you have like one job that completing it would cost more than dropping the penalty for dropping it off, then perhaps from business perspective you should drop off. Then, but you can reconsider it from considering as other factors. But it's all about properly building the cost and of the proper way of calculating the total cost of the solution. So because it's the cost is the final and the main factor which is taken into account when accepting or rejecting some interim solution while searching for it.
Right.
Excellent. Any other questions from anybody on the call? All right. Well, if nobody else has any questions, we'd like to just end with a couple of tidbits of information. If anybody would like, check out our YouTube channel. We have several other webinars and lots of great information on fleet management and other areas within the automotive industry and technology. So definitely check out our YouTube channel. You can also check out our blog for various insights. We have a lot of great information there too, a lot of great articles that you will find very useful, I'm sure. And for anybody who would like to get some more information and get some help or analyze what their business is, we are offering free 2-hour discovery calls. So this is a call with our project managers to talk about your business needs, technological challenges, processes, procedures, and everything that goes into setting yourself up for success. So definitely reach out to us if you have any questions and if you'd like to arrange for a one-on-one call so that we can go through your business needs and talk to you about how we can best help you. And if nobody has any other questions, then we're going to say thank you both.
Brian, I'm sorry to interrupt you. I think we have Isaac who has a question. Isaac, you can unmute and ask your question orally.
Hello.
Hi.
Yes, please, my question have to do with if with what he just presented. If someone want to implement or have an idea of that, how can the person get in touch, or is there anything that we can do?
Sure. Yes. I'm gonna send you. Well, first of all, we're gonna follow up with the recording. You will have this tomorrow in your inbox, and I'm gonna follow up with all the contacts that you can reach out to. And I think Brian would be delighted to talk about your needs and your idea.
Absolutely, Isaac. We can definitely arrange some time to speak.
Okay. Okay. Thank you very much.
You're welcome. Looking forward to it. Anybody else? Well, then I'd like to say thank you again to Sergey and Konstantin for sharing all that wonderful information. Very useful, a lot of knowledge and experience and expertise there. And we thank you everybody for your time and for joining us, and hope you have a wonderful day. So thank you everybody, and take care. All the best.